Buenas tardes, bienvenidos al Seminario de Divulgación Multidisciplinario. En esta ocasión tenemos un invitado especial y el doctor Salas nos va a hacer favor de presentarlo y de darle la bienvenida. Doctor, si me haces favor, te cedo la palabra.
Edgar, gracias. Gracias a todos. Well, last October 27, Otis surprised us as a Category 5 hurricane hitting the shores of Acapulco. And it was so because just 12 hours before, before making landfall, it was still a tropical storm. One may safely say that it caught most decision takers off guard. Today, the National Polytechnic Institute is honored to receive Ali Sarhadi, a climate scientist from the MIT Department of Earth, Atmospheric and Planetary Sciences, who can give us some clarity on what happened and what to expect. Ali specializes in processes related to anthropogenic global warming and their impacts on climate dynamics, including compound hazards involved in hurricanes in coastal cities, droughts, heat waves, and wildfires in wildland-urban interfaces. At MIT, Ali works with Kerry Emanuel's group, the leader in studying global climate and tropical cyclone activity. Before joining MIT, Ali held a postdoctoral research position at Stanford University, and he earned his PhD in civil and environmental engineering from the University of Waterloo. I met Ali Sarhadi about 1 year ago when he warmly welcomed me with a bowl of dessert similar to pinole. Over 1 year, he gave me some life-changing advice and introduced me to what are now mutual friends. He generously offered me frequent feedback on my research during my stay at MIT. I also was very fortunate to have the chance to attend a few of his presentations, when I was impressed by the clarity of his exposition, the beauty of his slides, and the importance of his line of research. Today, I'm most pleased to introduce Ali to the community of our research center. And in this talk, he will give us an insight into the topic of compounding extremes, their temporal and spatial dependencies, a methodology to evaluate the risk and the need for local action to reduce the damages inflicted by them. Ali, welcome, and you can now take it away.
Thank you so much, Joaquin, for your kind introduction. Hello, everyone. It's a great pleasure to be with you today. However, virtually, let me share my screen here. Today, I'm going to talk about intensifying compound extremes in a warming climate, and I'm going to emphasize on that compound extreme here, and I'm going to talk about typology of different compound extremes, risk, and also attribution of these kind of extremes. So let's start with definition of compound extremes. What I mean by compound extremes. So when two or more hazards occur simultaneously, they can form a compound event with much higher negative impact and environmental consequences. For example, in western part of the US, wildfires may occur simultaneously with droughts and heat waves. Or in eastern part of the country during landfalling of hurricanes, surge-driven flooding from high speed of hurricanes may occur simultaneously with rainfall-driven flooding in coastal areas, and they can form a compound surge and rainfall-driven flooding with much higher destructive potential comparing to each individual hazard. So these are some examples of compound extremes, and IPCC defines them as a combination of multiple drivers or hazards that contribute to negative societal and environmental impacts. So there are different types of compound extremes, and here I'm going to show you, three main types of compound extremes. The first type is temporally compound extremes or cascading extremes, and that is when one hazard or one climate extreme happens, and the impact of that hazard will amplify the impacts of the next hazard or extreme in the row. So as you can see, these are sequential extremes, and they are temporally dependent to each other, and they are called cascading extremes. And the second type is multivariate compound extremes, and that is when one hazard occurs simultaneously with another one, or the impact of one hazard will amplify the impact of another hazards at the same time. Sometimes neither of these hazards are considered to be extremes, but when they occur simultaneously, they may form a compound extreme with much higher, negative impact. And the third type is spatially compound extremes. Sometimes, climate extremes or compound extremes may occur in different parts of the world, which are not related to each other, but they may cause a negative, impact. For example, occurrence of climate extremes, hot and dry years in crop-producing regions in the world may cause sort of a food insecurity. So these are three main types of compound extremes. But during this talk, I'm going to focus on the two latter ones. And I try to show you how we can simulate and how we can quantify the risk of these compound extremes and try to address to what extent anthropogenic global warming has changed and will change the nature and the risk of these types of compound extremes. So in my research, I try to use different physics-based and climate dynamics theories to better understand, typology of these compound extremes. And I also developed some sort of multidimensional dynamic risk frameworks and also physics-based and numerical simulations by using, climate model simulations. And different types of downscaling to better address or quantify the risk of these compound extremes. And the output of my research could be used in the context of climate resiliency through different ways, such as, mitigation or adaptation. All right, during this talk, I'm going to talk about three different sections. In the first section, I'll talk about compound warm and dry years in crop-producing regions in the world. And in the second section, I'll talk about physics-based risk assessment methods to quantify the risk of compound flooding from hurricanes or tropical cyclones, especially in coastal areas. And also in the third section, I'll talk about the risk of economic damages from multiple hurricane hazards, again, in coastal areas. And if we have time, I'll talk about future research vision as well. All right, let's start with the first section. When we're talking about quantifying risk of compound hazards, one of the flexible tools that we use is copula functions. And copulas consist of, I think they are, multidimensional distributions, people call them. And they consist of two or more, marginal distribution, which fit to each individual hazards, and also a compound function or copula function, which models the dependence structure between two or more hazards. But the problem with currently used copulas is that they are stationary based, and that means all of their parameters are static and they're not changing through time. While we already know that climate change has altered the nature and the risk of these compound extremes. So what I do in my research is that to design a dynamic version of these copulas, which can evolve through time and quantify the dependent structure between two or multiple hazards, while accounting for non-stationarity through time arising from global warming. So in this way, we can quantify time-dependent risk of these compound extremes under a warming climate. So here I'm showing some results on the risk of compound warm and dry years, and more specifically, the risk of warm years in the first row, the risk or probability of dry years in the second row, and also the joint probability of warm and dry years. And here I define warm and dry years based on a baseline period, and we can quantify or come up with anomaly time series to define warm and dry years based on that baseline period. Here in the first column, I'm showing the results for aggregated global average, and in the last column here are the same results for different parts of the world that we have enough observations. And here I define risk as probability of occurrence of these extremes. So here in the first row, you can see the probability of warm years has been, almost 50% during 20th century. But after 1980, you can see that probability has increased, and it gets up to more than 85% in recent years. And as you can see, the distribution of warm years is shifting towards the end of the tail, and the same thing is happening in different parts of the world. But if you look at the probability of dry years, you can see it's almost 50% for aggregated global average, but it varies in different parts of the world. But if you look at the joint probability, you can see it increases from 20% during 20th century to up to 40% in 21st century. And as you can see, that risk has doubled in recent years. And as you can see, the same thing is happening in different parts of the world. And the innovative part is this part, actually. We can design these dynamic copulas, to quantify the risk of these compound extremes under a warming and changing climate. And then in the next step, I try to quantify the trend on the risk of these three different extremes. For warm year probability, dry year probability, and also joint probability of warm and dry years. So here you can see the magnitude of that trend for warm years in different parts of the world. You can see different colors showing, the magnitude of that changing trend. And as you can see, pretty much everywhere in the world showing an increasing trend on the risk of warm years. And for drier, you can see only tropical region showing an increasing trend for drier probability. But similar to warm year probability, you can see the trend has intensified pretty much everywhere for the joint probability for compound warm and dry years. And the second row here is the results for aggregated global average, but based on actual observations, which I talked about in the previous slide. But here in the last row, here I tried to answer a causality question. And the question here is that whether anthropogenic warming is playing a role here in intensifying the risk of these climate extremes or not. So to address that question, I tried to calculate the same probabilities by using climate model simulations based on two types of simulations. First, based on historical anthropogenic forcing simulations, in which we implement the effect of greenhouse gas emissions. And the second one is based on natural forcing simulations without any effect of greenhouse gas emissions. It's basically just natural variability. So here you can see I'm showing the results based on ensemble mean of different climate model simulations. And if you look at here, the results for historical based on historical anthropogenic forcing, you can see the trend that we're seeing here is quite in agreement with the trend that we're seeing in actual observations for warm years. But if you look at the natural forcing simulation results, you can see that the simulations are just fluctuating, around a constant value. And as you can see, the results are statistically significant from each other. So we can claim that anthropogenic warming is very likely increasing the risk of warm years pretty much everywhere in the world. And the results for drier probability, they're not different. And the reason is that the signal to noise ratio is pretty low for dryers. But if you look at the results for joint probability again, you can see that there is a significant difference between the results from historical anthropogenic forcing and natural forcing simulations. And we can claim that anthropogenic warming is very likely increasing the risk of compound warm and dryers pretty much everywhere in the world. And then in the next step, I was also interested in the spatial risk of these compound extremes in different parts of the world, which are responsible for food security. So here you can see crop producing regions in the world. And here, by spatial risk of these compound extremes, I mean the risk, and we define this as spatial risk as what is the probability or the risk. Here in the eastern part of the US, we experience a hot and dry condition. And what is the risk that the same condition happens in Europe in the same year? And the same thing between the US and China, US and India, US and Mexico. So you can see for each paired region here, we're going to have 4 dimensions instead of 2 dimensions. And for that, I went beyond a 2-dimensional dynamic copula, and I designed a 4-dimensional dynamic copula to quantify that spatial risk of these compound extremes between each paired region in the world. So basically, this is a probabilistic graph model, and by using that, we can quantify that spatial risk between each paired region in crop-producing regions in the world. So here I'm showing the results of the risk for over historical time period. So here, the thickness of each line represents the probability that each paired region simultaneously experiences warm and dry conditions. So as you can see, as time goes by, the thickness of these lines increases. And you can see that probability has intensified. And basically here, I'm showing the same results. If I'm going to give you an example here, you can see that the probability that, for example, western part of the US experiences a compound warm and drier with Australia is almost close to 0. But in recent years, that has increased up to more than 35%. And then I tried to answer that causality question again here, and I calculated the same probabilities based on anthropogenic forcing simulations and natural forcing simulations that I showed you. And here, over the last time period, you can see no symbol means that there is a significant difference between the results from anthropogenic forcing simulations and natural forcing simulations. So we can claim that anthropogenic warming is very likely increasing the spatial risk of these compound extremes in between each paired crop producing region in the world. And then the next question is that what happens if we follow the Paris Agreement and we keep the atmosphere temperature up to 1.5 degrees? Or no, we don't follow the Paris Agreement and the atmosphere temperature goes up to 2 degrees or 2.5 degrees by the middle of the century. So basically the difference is just 1 degree. And we're going to see how much that 1 degree increase in the atmosphere temperature will change the spatial risk of these compound extremes. So here I'm showing some results from 2020 until the middle of the century, 2050, for the risk of the spatial risk of, co-occurrence of hot years between each paired region. So here I'm defining that hot years based on, 4-time standard deviation of that baseline period that I talked about. So as you can see, if we don't follow the Paris Agreement, that 1 degree increase in the atmosphere temperature, you can see will significantly intensify the risk of the spatial risk of those hot years, occur between each paired region. And that risk will increase more than, 60 or 70% for the majority of the paired regions in the world. And also the risk that each paired region simultaneously experiences hot years and dry years and hot years and very dry years will significantly intensify if we don't follow the Paris Agreement, all because of that 1 degree increase in the atmosphere temperature. So as you can see, if we don't follow the Paris Agreement and we don't keep the atmosphere temperature up to a certain point, the consequences will be catastrophic in terms of water security and also in terms of food security. All right, this was the first section, and in the next section, I'm going to talk about physics-based risk of compound flooding from tropical cyclones or hurricanes. So when we're talking about hurricanes, there are multiple hazards involved, with hurricanes. The first hazard, which you experience actually in Acapulco, is the strong winds. Winds are quite risky and they cause lots of damages to buildings. And the reason is that most of the buildings are not even designed to withstand, strong winds from hurricanes. And that's why wind is risky and it causes lots of damages to coastal cities. And the second hazard is freshwater flooding. So to give you an example, during Hurricane Mitch in 1998 in Central America, more than 8,000 people were killed, all from fresh water and none from wind. And the real killer, though, is the storm surge. So here you can see what it did to New Orleans from Hurricane Katrina. And hydrodynamically, storm surge is the same as tsunami, although it is generated by high-speed winds rather than shaking seafloor. So this is a storm surge, and no one can survive it. But sometimes these multiple hazards may occur at the same time. And for example, high-speed winds from hurricanes may cause, surge-driven flooding in coastal areas. And also right after landfalling of that hurricane, we will get heavy rainfall-driven flooding in inland areas. But sometimes these two hazards may occur simultaneously, and they can form a compound surge and rainfall-driven flooding with much higher destructive potential comparing to each individual flooding hazard. So in this section, I'm going to talk about these compound flooding events, and I try to show you how I try to simulate that compound flooding events and how we can quantify the risk of these compound flooding events from hurricanes under a warming climate by using physics-based risk assessment modeling. So we've done this for multiple coastal cities in the US, but here I'm going to focus only on New York City and try to show you some results for that city. So if you look at all of historical records from hurricanes passed through New York City or its area, this is all the information that we can get. So you can see this information is pretty, it's not lots of information. It's pretty narrow information, and the information is flawed. And we cannot, if we do any risk assessment for compound flooding, it's going to be lots of uncertainty. And even if we have lengthy records of from these hurricanes, even lengthy records, they do not represent actually even current climate. And the reason is that climate change has already happened. And even today's climate information or records are not going to be a good guide for future decades, again, because of climate change. So to address the lack of information that we have from hurricanes in coastal cities, so here we try to use a physics-based method. So in this method, we use sophisticated hurricane models, which are coupled atmosphere and ocean models. And through this model, we can randomly seed the entire Atlantic Ocean. And then when the wind speed of each seed gets up to a certain wind speed, let's say 40 knots, that will form a hurricane. And then depends on the thermodynamic of the ocean and atmosphere, that hurricane may evolve through time and space. So in this way, we can simulate a synthetic hurricane by using a sophisticated hurricane model. And then we can take this sophisticated hurricane model and we embed it in climate model simulations. And by using the key drivers or the key factors from these climate model simulations, we can sort of downscale these synthetic hurricanes. And in this way, we can generate thousands of these synthetic hurricanes for the past climate, for the current climate, and also for the future climate. So in this way, we can, come up with thousands of these synthetic hurricanes passing through New York City. And in this way, we can address the lack of information, lack of data that we have for hurricanes in the current climate and also in the future decades. And then these synthetic hurricanes could be used as a basis to quantify the risk of compound flooding that I talked about. All right, as I mentioned, compound flooding consists of two components. The first one is rainfall-driven flooding, and the second one is surge-driven flooding. So again, we use these synthetic hurricanes as the basis to quantify each component. Here, by using these synthetic hurricanes and some, tropical cyclone rainfall models, we can simulate rainfall intensity coming from each synthetic hurricane for that area. And then by developing a hydraulic model, we can convert that rainfall intensity into the level of flooding on the ground. And we do that by using a continuity equation to quantify the level of flooding at each grid cell. And here, for example, the volume of flooding coming from rainfall intensity in each grid cell, at time t plus delta t is a function of the volume of flood from previous time plus incoming fluxes from different edges plus incoming rainfall from hurricane minus infiltration for that specific grid cell. And then through a momentum equation, we can quantify how that water in each grid cell can flow between different grid cells. So in this way, we can translate rainfall intensity coming from hurricane to the level of flooding on the ground and address rainfall-driven flooding. And the second component, which is interesting, is storm surge or storm surge-driven flooding. So to simulate the storm surge, again, we use the synthetic hurricanes, and we use the key drivers of a storm surge, which are wind speed from hurricane and also sea level pressure. So by having these two drivers from hurricanes, we can use a hydrodynamic model called GeoClaw, and GeoClaw uses multi-layer shallow water equations to simulate a storm surge height in coastal areas during landfalling of that hurricane. And in this way, for any area along the coastline, I'm showing them actually in by using some synthetic gauges. So in any location along the coastline, we can simulate surge height during landfalling of each synthetic hurricane. Here, there is another factor which is important, and that is sea level rising. What will happen in the future decades with anticipated actually sea level rising, how much that storm surge will intensify. So here I incorporate that sea level rising, simulated sea level rising to the model, to see the effect of even sea level rising in storm surge modeling by incorporating that by using a bathtub approach. All right, in this way, we can address the second component of compound flooding. But when I'm talking about compound flooding, for compound flooding itself, what I do is that I use simulated storm surge along the coastline, and also rainfall intensity coming from hurricane in inland areas as simultaneous boundary condition for that hydraulic model. And in this way, I try to simulate compound surge and rainfall-driven flooding. And basically, I can simulate any interplay or interaction between surge and rainfall-driven flooding in coastal areas. So here I'm showing an animation, to show you a simulation for compound flooding from a hurricane called Hurricane Sandy, which made landfall in New York City and New Jersey in 2012. So here on the right panel, you can see wind speed from that hurricane. And on the left panel, and the unit actually here is mile per hour. And on the left panel, I'm going to show you simulated compound flooding from that hurricane in meter. Actually, each color here represents the level of compound flooding for coastal areas. So here you can see before landfalling of that hurricane, high-speed winds from that hurricane, as you can see here, may cause surge-driven flooding in coastal areas. So here you can see that surge-driven flooding in meter. And then right after landfalling of that hurricane, you can see, we see, rainfall-driven flooding. But there is a quite nonlinear interaction between surge and rainfall-driven flooding in coastal areas, which forms compound flooding. So basically, salty surge-driven flooding comes in, and we have freshwater rainfall-driven flooding comes in from upstream, and there is quite nonlinear interaction between or interplay between rainfall and surge-driven flooding, which forms compound flooding with much higher destructive potential for coastal area. So in this way, we will be able to simulate compound flooding with high spatial and temporal resolution. Even with less than a minute, we can simulate that compound flooding. So in the same way that I showed you, we can simulate compound flooding from thousands of those synthetic hurricanes that I showed you. And we can come up with thousands of these compound flooding map for each synthetic hurricane. And then the next question here is that how much the risk of compound flooding may change under a warming climate. So here I try to address that scientific question, and I try to quantify the contribution of two primary drivers here. The first primary driver is a storm climatology change. Basically, any changes in wind, rainfall of these synthetic hurricanes under a warming climate, we refer it to storm climatology change. And the second driver is sea level rising. And here I'm trying to address the contribution of these two primary drivers on changing the risk of compound flooding in the future, in the current and also in the future decades. So here in this graph, each dot here represents simulated compound flooding level for a specific coastal area in New York City. Each line represents simulated results for each climate model simulation, and here blue color represents the results for the current climate, orange for the middle of the century, and red for the end of the century. So here I'm showing the results of compound flooding level in meters in y-axis and x-axis showing return period, which is calculated based on exceedance probability. So here, this dashed line represents the maximum compound flooding level from that hurricane that I showed you in the previous slide, which was Hurricane Sandy in 2012. So here you can see this dashed line represents that water compound flooding level for that hurricane. And in this way, I can quantify the risk of compound flooding from that Sandy-like hurricane in the current climate based on the results from these blue lines. And you can see the return period of such a destructive hurricane or compound flooding from that hurricane is 200 years based on the results from current climate. So that means in the current climate, we're going to experience such a destructive hurricane once every 200 years. And as you can see, that return period will decreases up to 170 years by the middle of the century and 130 years by the end of the century. Basically, you can see that risk will intensify only when we consider storm climatology change. But when we consider or add the effect of sea level rising, we're seeing a totally different story here. You can see the risk of such a destructive Sandy-like compound flooding event is going to be 150 years in the current climate, and that will reduces up to 60 years by the middle of the century, and up to 30 years by the end of the century. So that means by the end of the century, we're going to experience such a destructive event, once every 30 years. And as you can see, the risk will be 5 times more than the risk that we are experiencing in the current climate. So basically, as you can see, sea level rising will significantly intensify the risk of compound flooding in coastal areas in New York City in the future decades, comparing to any changes coming from storm climatology. And in the same way, we can quantify a spatially varying risk of compound flooding events for different return periods for the middle of the century and the end of the century. And here I'm showing the results for those events which occur once every 100 years. And here you can see the results by the end of the century comparing to the current climate. When we consider storm climatology change, when we consider, joint effect of storm climatology change and also sea level rising. So you can see by the end of the century, in coastal areas, we're seeing, that intensification in the level of compound flooding. Basically, this is extra compound flooding level that we're going to experience by the end of the century. It gets up to like half a meter in coastal areas, and we're seeing intensification of rainfall-driven flooding, which is coming from more intensified rainfall in inland areas. But when we add the effect of sea level rising, you can see that extra compound flooding level that we're going to experience in coastal areas will get up to more than 1.5 meter, for those areas when we add that effect of sea level rising. So as you can see, sea level rising will significantly intensify the risk of compound flooding from hurricanes as the climate warms in the future decades. All right, in the last section, I'm going to talk about the risk of economic damages from multiple hazards from hurricanes. So to quantify the damages from winds, strong winds of hurricanes, we use a damage function here, which empirically models the relationship between wind speed and also the damages or fractional property value lost. So here, through this animation, I'm going to show you the relationship between strong winds with damages or fractional property value loss over different categories of hurricanes. So as you can see, when wind speed increases, you can see at a specific threshold, damages to that property starts, and we call it V threshold. And then with higher wind speed in higher categories, you can see at a specific threshold, half of that property is gone. And we call that V half. And with higher, strong winds, you can see all of that property is gone. So basically the idea here is that if we can tune these two thresholds, we can tune this damage function for any areas with any building codes or resiliency. So here I try to basically optimize this damage function for some grid cells that you can see here over New York City with the size of 5 kilometers in 5 kilometer. Here I try to optimize this damage function, basically reduce the difference between observed damages with predicted damages. So here again, by using some physics-based methods, we can simulate high-speed winds from historical hurricanes. And by using some physics-based augmentation methods, we can increase the number of those synthetic hurricanes, which are pretty similar to those historical hurricanes. So even with that increasing the number of samples, it's really hard to optimize these damage functions. And the reason is that we have lack of information from historical records. So here, the way that I optimize this damage function actually is to use some conditional random field models. Basically, this random field model consists of two functions. One unary function, which models the relationship between xi with yi. Xi represents wind speed and yi represents damages in each grid cell. Actually, each dot here represents one grid cell here. And then the second function is a pairwise function. By using that unary function, I can model the relationship between wind speed and damages in that target variable by using a simple neural network. But I use another function here through this CRF model, which is called pairwise function. Basically, I can use the spatial information from surrounding grid cells as input to a deep learning model, and try to, by using those spatial information for damage, try to optimize that damage in that target grid cell. So basically, these two functions are working simultaneously for each grid cell, and also I'm optimizing these damage function in each grid cell, in all of these grid cells simultaneously. And in this way, I can come up with optimized damage function for each grid cell for New York City. So here you can see the results in terms of evaluation or performance of these models for some historical hurricanes which occurred in New York City, and as you can see, the accuracy is pretty high. And here the idea is that I can simulate thousands of these synthetic hurricanes for the future decades by the middle of the century or the end of the century. And I can simulate maximum wind speed in each grid cell. And by replacing that in these optimized damage function, I can quantify fractional property value loss. And by having total property values, I can quantify monetary losses from wind speed of these synthetic hurricanes for each grid cell and also for the entire area. And we did this, and we simulated, wind-driven damages and quantified wind-driven damages for thousands of these synthetic hurricanes, and we can come up with this graph here. You can see which represents, the monetary damages, wind-driven monetary damages in x-axis, and y-axis represents, return period. And blue color here represents the results for the current climate, again, orange for the middle of the century and red for the end of the century. So here, for example, for those events which occur once every 200 years, the damages, monetary damages that we're going to experience, wind-driven damages from these hurricanes for the entire area will be $1 billion. And by the end of the century, it'll increases up to $1.5 billion. And by the end of the century, it'll get up to $2 billion. So as you can see, the wind-driven damages will significantly increase as the climate warms. And we can do the same thing for compound flooding, damages. I showed you how I try to simulate those compound flooding, and basically we can develop those damage functions for compound flooding events as well. Here I'm showing the results for compound flooding damages from hurricanes in the current climate by the middle of the century and the end of the century. And again, if we choose, let's say, those events which occur once every 200 years, the damages that we're going to experience from compound flooding in the current climate for that type of events is almost, less than $20 billion for the entire area. And that will increase us up to more than, $25 billion or less than $30 billion by the middle of the century, and almost $40 billion by the end of the century. So as you can see, as the climate warms, the damages coming from these intensifying compound flooding events from these hurricanes will significantly intensify. And the same way we can come up with joint return periods, to quantify how much of the damages are coming from, compound flooding, and at the same time, how much of the damage is coming from wind. And obviously, as I showed you, that the damages coming from, compound flooding are much higher than wind-driven damages. All right, so some takeaways from these three sections. Here I try to convince you that we need to, advance physics-based risk assessment modeling to better quantify, the risk of these compound extremes, and try to move away from statistical based, risk assessment methods, which are based on historical records, and basically they are flawed and they are quite uncertain. And we need to try to translate a climate risk of these compound hazards or compound extremes into actual damages in the way that I showed you in the last session. We try in this way, if we do that, we can better understand and mitigate the consequences from these, compound extremes, and also consequences from global warming. And we need to understand that anthropogenic warming presents an immediate and severe risk to occurrence of these destructive compound extremes. And we need to definitely acknowledge, the global impact of climate change, and at the same time try to act locally. In the first section, I tried to show you how we can implement larger scale mitigation strategies and keep the atmosphere temperature up to a certain degree to reduce the damages arising from those compound warm and dryers. And in the two latter sections, I tried to show you that we need to enhance the resiliency of our communities or our coastal cities, if we are going to minimize the damages arising from these intensifying climate extremes. I have some slides, to show you, but I think I will stop here, and I'll be happy, to take your questions.
Ali, thank you. Thank you very much for your talk. And now we open the mic for whoever wants to ask a question. In the meantime, I would like to start with one question. So you mentioned the importance of applying advanced modeling techniques. However, when Otis arrived, we realized that none of our models, apparently, it was able to predict what was going to happen. What do you think that is needed in terms of science and technology to improve our current forecasting performance?
Sure, that's a very good question, and in terms of forecasting the tracks of hurricanes, we have done a very good job, nowadays, and our models are really good. And also in terms of predicting the intensity of hurricanes, I think the models are not too bad. But in terms of rapid intensification that we saw during Hurricane Otis, our forecasting models are worse. And the reason is that we do not have sort of real-time observations. And we have, satellite-based records for, let's say, sea surface temperature, but we do not have any real-time, information for deeper layer of the ocean. So I think I have one slide here to show you what happened during Hurricane Otis. So here you can see, during that hurricane, any hurricane, basically, when we have warm waters in sort of top layers of the ocean, that feeds actually that hurricane. But in deeper layer, if we have cooler deep water, that circulation basically brings that cooler deep water to upper levels, and what happens that a hurricane gets weakened, and that is not going to intensify because of those cooler water on top layers. But when that circulation brings actually warmer deep water to top layers, basically that will feed that hurricane, that evaporation that happens from those top layers, and the hurricane gets stronger and stronger. Basically what happens during a Hurricane Otis was this, and all of the forecasting models actually failed because they didn't have real-time information for that circulation or the temperature from deeper layers, and a rapid intensification happened during a very short time, and that left everybody with limited time to evacuate, which was an extraordinary hurricane, and no one has seen actually for Mexico.
All right. Perfect, thank you. Now, I wonder if there are questions from the audience. Edgar.
Thank you so much. Thank
Yeah.
you for your presentation, Ali.
Yeah.
I have two questions.
Yeah.
Oh, I will lower the hand. Okay. The first one is about anthropogenic versus natural global warming. I mean, I think it's a natural kind of cycle that is making the kind of natural warming, and also the anthropogenic, what we can cause that kind of global warming. How much is our fault? How much is natural? I know. Is it possible to make a difference? Because how much of that global warming is really anthropogenic? And the second question, it's about, okay, first that and then the other.
Yeah, I'll answer your question first. So yeah, I mean, the way that we quantify the contribution of anthropogenic warming is by running these climate model simulations. I showed you, we can implement, the effect of a greenhouse gas emission in those simulations and see how much, in a warming climate, that warming climate basically changes the nature and the risk of these sort of compound extremes, and at the same time you can run these climate models without any effect of greenhouse gas emissions. But if you're asking specifically, let's say for like the possibility or probability of occurrence of Hurricane Otis, for example, in Acapulco, with or without the effect of greenhouse gas emission or anthropogenic forcing, that's pretty complicated, and we need to have more information to address that for each individual event. It's not easy to answer it. This much of the contribution is coming from global warming, and this much is natural. In terms of each event, it's really hard to answer it. But when we're talking about the trend or long-term trend, I think that is possible, to address how much the contribution is coming from global warming in the way that I showed you actually in the first section.
Okay, and that okay, Dr. Ali, that leads me to the other question that is about you use deep learning models to do some calculation and simulations. As far as I know, those need kind of tons of data. And I think that's the first problem. Get, like you say, the information, the data, the specific data. So I'm wondering if there is some kind of, there is a data, you use this to train the network and use this to validate. Is how accurate it is? First, I think you perform some kind of that validation process to figure out the average error, the mean square, or something like that of your model, and how accurate you are expecting to be that model, that trained model, in the short. Okay, in the short term.
Yeah, sure. I mean, and in terms of modeling that you mentioned, definitely, yeah, we need information from past hurricanes in terms of hazard and also in terms of damages coming from each hazard. I showed you wind-driven damages, and I modeled that through that deep learning, and the same thing for compound flooding. The way that I showed you, by using that physics-based model that we have, a sophisticated hurricane model that we have, we can reconstruct actually those synthetic hurricanes, which are quite similar to actual historical, hurricanes. So in that way, we can come up with hazards which are pretty much similar to the actual hazard, in terms of wind and in terms of, compound flooding. And we evaluate that model by using the, real evidence. When we're talking about like, compound flooding, we have some information or records during that hurricane, during Hurricane Sandy, and we can evaluate the performance of our physics-based model. But here I'm showing the relationship between damage and the hazard, and basically we're trying to model the damage part, right? And the way that I evaluate our model is based on cross-validation approach. We can leave the damages coming from one hurricane out, and we can train our model, and then we can test it based on that unseen damages from that leave on sort of hurricane. So in this way, you can try at least to see how much you can predict the damages from that unseen damages from that hurricane. So in this way, we evaluate our models. But yeah, as you mentioned, the damage information that I'm using is based on current climate, right? But what happens in the next, decades, by the middle of the century and the end of the century, about the resiliency or building codes of different neighborhoods in New York City, we don't know. That's the assumption that we make, based on current climate, building codes. But yeah, who knows? Maybe in the future decades, they will come up with some, resilient buildings that any type of like hurricane cannot make any like damages to that kind of buildings. Yeah, that's kind of assumption that we will make here.
Perfect.
Yeah.
Well, thank you very much. I think that we ran out of time. Ali, I would like to thank you very much from the National Polytechnic Institute. Thanks for your time and your clear and beautiful explanation about this phenomena. And thank you very much. And I hope to see you soon.
Thank you.
Again.
Thank you. I really enjoyed my time being with you.
Thank you. Edgar, thank you very much. You can take it away now.
Have a good night.
Thank you, Dr. Ali. Wait a second. I'm going to tell this part in Spanish because it's part of the protocol.
Sure.
And it's only thank you and a document, and I need to read. So, el Instituto Politécnico Nacional, Centro de Investigación en Ciencia Aplicada y Tecnología Avanzada, Querétaro, entrega el siguiente reconocimiento al Dr. Ali Sarhadi por su participación en el Seminario de Divulgación Multidisciplinario de este centro con la conferencia Intensifying Compound Extremes in a Warming Climate. Esta actividad de divulgación está dirigida a la población estudiantil de las diferentes disciplinas del centro, así como al público en general que desea asistir o enlazarse a través de nuestras redes sociales. Querétaro, 14 de noviembre del 2023. Firma Dr. Juan Bautista Hurtado Ramos, director. Thank you so much, Ali. Thank you for your time. We appreciated your very interesting presentation. Thank you
so much. Thank you. Have a good night.
You too.
Good night too.